Hey everyone! If you're a future environmental scientist, agronomist, or land manager, you are in exactly the right place. Welcome to today's Explainer. Now, in your undergrad soil science classes, you usually focus a ton on what makes soil fertile, right? Well, today we're flipping the script. We are going on a mission to diagnose a silent, invisible disease that is literally suffocating the Earth's agricultural skin.
Think about this for a second. How do you actually track a crisis that destroys entire crop yields but completely hides beneath the soil surface until it's way too late? I mean, unlike a massive forest fire or a flood, soil salinization just creeps in super quietly. By the time a farmer actually sees those white salt crusts popping up on their fields, the damage is already done. It's massive. So how do we catch it beforehand?
Well, here is our flight plan for today's mission. First up, the soil salinity crisis. Second, field tests versus satellites. Number 3, we'll meet the Sentinel-2 satellite. Fourth, how satellites see salt. And finally, number 5, saving our agricultural future.
All right, let's jump straight into Section 1, the soil salinity crisis, and how we go about diagnosing Earth's disease.
Okay, so if you spent any time in your field labs, you probably already know that we quantify this disease using electrical conductivity, or EC. You literally measure this using a water solution or a direct soil probe, and we record it in decisiemens per meter. Now, the golden rule you need to remember is that any reading over 4 establishes a baseline that the soil is heavily salt-affected. But here's the crazy part. Even slightly salt-affected soils below that threshold can really wreck plant growth depending on the irrigation setup.
And here's why salt is just absolutely devastating to a plant's biology. When soluble salts build up in the crop root zone, they spike the osmotic pressure. So what does that actually mean for the plant? Well, it essentially triggers what we call a physiological drought. It literally restricts the plant from taking up water. It's choking off the plant's ability to drink, even if the roots are sitting right in the water. Add in some severe nutrient imbalances, and you end up with massively stunted crop yields.
Moving right along to Section 2, field tests versus satellites. Or, as I like to call it, the biopsy versus the MRI.
Now, as an undergrad, you're definitely going to learn how to take a proper soil sample. And don't get me wrong, that is absolutely vital. But I want you to contrast the really grueling, expensive process of walking a huge field with a soil probe, which is basically a highly accurate but super localized biopsy, with the instant county-wide scan we get from remote sensing. Satellite imagery is incredibly fast, it covers massive spatial scales, it acts exactly like a full-body planetary MRI, letting us do multi-temporal monitoring. Basically, we can watch things change over time without ever stepping foot in the mud.
And this crucial point was perfectly summed up by Lee and colleagues back in 2015. They noted that traditional methods of field surveying and sample analyzing just aren't adequate to frequently cover large tracts of land. Simply put, if we want to monitor really rapid environmental shifts, especially in coastal zones getting hit by climate change, those old manual methods just can't keep up. We need scale, we need frequency, we need satellites.
Which brings us right to Section 3. Let's meet the Sentinel-2 satellite, the ultimate Earth doctor.
So let's pit the European Space Agency's Sentinel-2 against the classic Landsat 8 satellite. The numbers really speak for themselves here. Sentinel-2 gives us a stunning 10-meter spatial resolution, compared to Landsat's 30 meters. But honestly, even more important for tracking a fast-moving threat like soil salinity, Sentinel-2 has a super quick 5-day return time, whereas Landsat takes 16 days. That means we get a brand new, high-res scan of our patient, the Earth, every 5 days. For predictive skill and high-frequency mapping, it's just undeniably superior.
And Sentinel-2 has a bit of a superpower. It offers global coverage and high-resolution optical images over a really wide electromagnetic spectrum. This means it's not just spotting the obvious white salt crusts on bare dirt when things are already at their worst. By tracking vegetative anomalies, it detects the subtle physiological stress happening in the crops above ground. It literally sees the plant struggling long before our own human eyes ever could.
Okay, Section 4, how satellites see salt, or unlocking the light math.
Now, do not let this formula freak you out. This is just what I like to call light math. This specific equation is for the Normalized Difference Salinity Index, or NDSI. Think of it as a recipe. It subtracts and divides invisible shortwave infrared bands to basically isolate the mineral salts. When you run this calculation on the satellite pixels, the salt literally starts to glow on your digital map. It's amazing. Because different materials bounce light back in completely different ways, we have to look across the whole spectrum of salinity. The visible to shortwave infrared range is really vital for spotting those whitish salt crusts on bare soil. But when you isolate specific bands, like shortwave infrared 1 and 2, that targets the diagnostic absorption features of hydrous mineral salts. Meanwhile, the near-infrared bands help us track moisture gradients in the canopy and soil. It's kind of like putting on 3 different pairs of specialized glasses all at the exact same time. So, as future geospatial analysts, here is your actual step-by-step workflow in the lab. Step 1. Your satellite captures the multispectral image. Step 2. You apply a spectral index, like the NDSI we just talked about, or a brightness index. Step 3. You cross-reference that with your in-situ ground data, your biopsy, and feed it all into a machine learning model. And finally, Step 4. You generate a highly accurate, high-resolution soil salinity map. Bam! All right, let's wrap things up in Section 5, saving our agricultural future, taking all this from data to action.
You guys are inheriting a planet that is in the middle of a massive transition. As sea levels rise, accurately monitoring soil salinization is going to be absolutely critical to protecting our coastal agricultural lands. This invisible disease is spreading. Continuous satellite monitoring isn't just some cool academic science project anymore. It is an absolute necessity for the survival of our food supply.
When you enter your careers, mastering these tools translates to massive real-world impact. It means you can optimize irrigation and drainage for farmers. You can fill in critical data gaps for decision-makers. You'll be able to differentiate heavily affected, dead soils from zones that are just naturally full of salt-tolerant halophytes. And even cooler, you can combine this optical data with radar from the Sentinel-1 satellite, which lets you monitor the soil in literally any weather condition, even straight through the clouds.
So as you master this incredible remote sensing tech during your undergrad journey and beyond, I want to leave you with one ultimate question. With these amazing satellites continuously scanning the Earth's health right now, floating up there waiting for your commands, what other invisible environmental crises will you uncover before they surface? Thank you so much for joining me for this explainer today. Keep asking those big questions, and I'll catch you next time.